Hi, everyone. Welcome and good evening. My name is Lauren Artilles, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm honored to introduce this virtual event with Marcus du Sautoy, presenting his latest book, Thinking Better, The Art of the Shortcut in Math and Life, in conversation with Melissa Franklin. I hope everyone's week is off to a good start. Thanks so much for joining us virtually. Tonight's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. Coming up in the series on Wednesday, November 10th, we'll host acclaimed engineer Ritu Raman for her new book, Biofabrication. To learn more about this and our other upcoming virtual events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more info. We also have a Science Research Public Lectures YouTube channel where you can view previous talks that you might have missed, and I'll be sharing the link to that in the chat shortly. This discussion will conclude with some time for your questions. So if you have a question for our authors at any time during the talk, just click on the Q&A button on your screen, and we'll get through as many as time allows. In the chat, I'll be posting a link to purchase Thinking Better on harvard.com, as well as a link to donate in support of this series and our store. Your purchases and financial contributions make events like tonight's possible and help ensure the future of a landmark independent bookstore. So thank you so much to our partners at Harvard University, and thank you to all of you for showing up and tuning in support of authors, publishers, indie bookselling, and especially for science. Finally, as you may have experienced in previous virtual gatherings, technical issues may arise. So if they do, we'll do our best to resolve them as quickly as possible. Thank you for your patience and understanding. And now I am delighted to introduce this evening's speakers. Marcus du Sautoy is the Simonier Professor for the Public Understanding of Science and Professor of Mathematics at the University of Oxford. He has presented numerous radio and TV series, including a 4-part landmark TV series for the BBC called The Story of Maths. He works extensively with a range of arts organizations to bring science alive for the public, from the Royal Opera House to the Glastonbury Festival. And he's also published and starred in the play I Is a Strange Loop, which was performed at the Barbican in London. He received an OBE for services to science in the 2010 New Year's Honors List and was made a Fellow of the Royal Society in 2016. Melissa Franklin is an experimental particle physicist who studies proton-proton collisions produced by the Large Hadron Collider. And born and raised in Canada, she received her BSc from the University of Toronto and her doctorate from Stanford University. She worked as a postdoctoral fellow at Lawrence Berkeley Lab, was an assistant professor at the University of Illinois Urbana-Champaign, and was a junior fellow in the Society of Fellows at Harvard before joining the Harvard faculty in 1989. Tonight, they'll be discussing Marcus's latest book, Thinking Better, which celebrates the mathematical art of the shortcut and the diverse ways the world has been impacted by simplifications of work made possible by math. David Schwartz calls Thinking Better an engaging, delightful adventure through a variety of situations where mathematical thinking, in particular the search for clever shortcuts, illuminates deeper mathematical truths. And Roger Highfield says, Marcus du Sautoy has created a smart, well-written, and entertaining guide to the connecting tunnels, underpasses, and other tricks we can use to traverse the trials of everyday life. Without further ado, I'm excited to turn things over to our speakers. The digital podium is yours, Marcus and Melissa.
Wonderful. Great. Well, wonderful to be joining you from here in London, where it is dark and nighttime, but the wonderful shortcut of Zoom is bringing me to you to talk about the book, and also great to be with Melissa. So hi, Melissa.
Hi. I totally loved this book, and I wanted to know if you wanted to tell us a little bit about the book first before we went into more details.
Cool. Yeah. Let me give you a little bit of about the book. I think it's interesting. I'm sure that every scientist that you've had as part of this series of talks probably has one teacher or somebody who inspired them to sort of go on their journey to become that scientist. And actually, the book starts with the mathematics teacher that inspired me to choose mathematics as a subject I would dedicate my life to. And he told us a story when I was about 12 or 13 in our class, which kind of captures the spirit of this book. And it's a story that any mathematicians out there in the audience will know. It's kind of one of our fairy tales. It concerns one of our great heroes in mathematics, Carl Friedrich Gauss, 19th century mathematician. But this is Gauss as a 9 or 10-year-old sitting in his class, and the teacher of his class asks the class to add up the numbers from 1 to 100. I think the teacher thought, well, this is going to take all the students a long time to do, probably make lots of mistakes on the way. But even before he'd finished asking the question, Gauss had written down a number on his little slate board and slammed it down on the desk in front of the teacher. And the teacher thought he was being a bit impudent, but then looked and saw the correct answer there and said, well, how did you get that answer so quickly? And Gauss said, well, there's a shortcut. I mean, I can see all my fellow students, they're starting at the beginning and adding 1 and 2 and 3 and 4. And it's just going to take them ages till they get to 100. But I spotted this shortcut, because if you combine the beginning and the end of the journey, I could add 1 plus 100, that's 101. 2 plus 99, that's also 101. 3 plus 98, 101. So Gauss had recognized that there were 50 pairs of numbers adding up to 101. So he realized, well, that's 50 times 101. The answer is 5,050. And when I heard this story, I thought, wow, that's the subject I want to dedicate myself to. And my teacher said, that is what mathematics is about. It isn't about long division to lots of decimal places. I think that's what most people think I do as a research mathematician here in Oxford. No, it's actually about finding the clever way to look at a problem, stepping back and finding a kind of shortcut to be able to do that calculation without doing a lot of hard work. And I think for me, I was a lazy teenager. I think that just so appealed to me, the idea that, well, you can avoid doing lots of boring, hard, laborious work by just stepping back and thinking cleverly about a problem. And my teacher said, yeah, that is what mathematics is about. Mathematics, he liked to call the art of the shortcut. And so this book that I've written, which starts with that little story of Gauss, is really kind of a collection of all the wonderful shortcuts that we mathematicians have kind of amassed over 2,000 years of thinking. Shortcuts like the calculus, or the power of a diagram to produce a shortcut, or the idea of looking for a pattern. So hopefully this book is going to be your shortcut to the kind of world of the shortcut. But there are a few things which are important here, because this is not about cutting corners. So I think shortcut has a little bit of a pejorative sound to it sometimes. And for me, that this is about getting to your destination, getting to your goal successfully, but as efficiently and quickly and cleverly as possible. And there's also another distinction here that's important. Although I was a lazy teenager and liked to avoid work, actually, there's some work I really enjoy doing. I enjoy being a mathematician. So the point about these shortcuts is not to avoid doing any work, because I think work gives us value, but it's about avoiding the work you don't really want to do, the kind of boring work. So in fact, Aristotle already identified kind of 2 different sorts of work. Praxis, work for its own sake, the work you love doing, and what is called poiesis, which is work to get to a goal. And that's, you just want to get to the destination in order that you can do the things you want to do. So in a way, my book is trying to say, here are the shortcuts to avoid all the boring work that you don't want to do. So you can then get to the destination where you can do the things you do want to do. And it's interesting, I actually found an interesting quote by Karl Marx. Interesting, I didn't expect to be quoting Karl Marx in a book about mathematics. But he wrote, in a higher phase of communist society, labor has become not only a means of life, but life's prime want. And I think the point is that these shortcuts are helping you to take yourself out of the realm of necessity, as he called it, and find yourself in the realm of freedom. So these shortcuts are trying to get you to the place where you spend your time doing what you want to do. Now, there's also another interesting inspiration for this book, which is the previous book that I wrote, which was actually published by Harvard University Press. which was about the kind of emerging power of artificial intelligence. And in particular, I wrote a book called The Creativity Code, which is showing how artificial intelligence, which has been in kind of decades of winters, is suddenly in a heat wave where it's being able to do extraordinary things because of machine learning. And so the book is about how AI even might be able to be creative, both in a literary way, musical, painting and things. And I did an interview with a journalist here in London. And by the end of the interview, he was so depressed that, what is there left for humanity to do? And so I had to think of some way to cheer him up. So I said, what is it that we humans are good at that computers are not good at? And what I realized is that laziness that I had as a teenager can actually sometimes be a useful trait, because a computer does not get tired. It's not lazy. It can just keep on churning. If it wants to count from 1 to 1,000,000, 1 to a zillion, it just can keep on going. But, if the teacher had said, right, Gauss, you got to 100, now I want you to get to 1,000,000. The beautiful thing is that trick that he came up with works just as well from 1 to 1,000,000. He compared the numbers up. These shortcuts are just clever ways of avoiding the hard work. So my feeling is that actually our saving grace is a little bit about our laziness, where we say, I don't want to do a lot of hard work. I want to find some clever way to look at a problem and take a step back. And I think often that desire to find a clever way to solve a problem can often lead us to find new ways of doing things, new thinking. So this book is a sort of counter book to the AI book. The sort of what we got over the AI is that we don't want to go through the number crunching that an AI can go through, but sometimes we had to find clever ways to do this book. Now, the title as well might make people think a little bit about another book. There we are, Thinking Better, because there's a very famous book by Kahneman called Thinking Fast and Slow, and slightly bouncing off that title as well, because Kahneman illustrates that our fast intuitive thinking often leads us to make mistakes, the kind of system 1 thought process. And he explains, well, we've developed this system 2 thought process, the slow thinking, which is, to carefully think about analyzing a problem. I mean, here's a little puzzle for you. You can put the answers in the chat, maybe. My book costs $10 plus half its price. How much does my book cost? Now, your system 1 fast thinking might get you a quick answer, but you'll probably find it's wrong, and you have to do a system 2 slow analysis, which might use a little bit of algebra, one of the shortcuts in the book, to get to the right answer. But what I felt was Kahneman's kind of, analytic thinking does not have to be slow. So it can be fast, and these shortcuts are getting you to answers where you don't have to kind of think too slowly about it. So my hope is that this suite of shortcuts that we put together, and which I talk about in the book, is actually showing that humanity's come up with clever ways to think about things in an analytic and sort of system 2 way. So this book, I hope, it took us 2,000 years to come up with these things. One of the messages is shortcuts are sometimes take a long time to find, but we've found all these wonderful shortcuts. So my hope is the book is somehow the reader's shortcuts to this 2,000 years of shortcuts. And I guess just to say another last thing before I hand back to you, Melissa, is I've also wanted to look at other professions to see whether they had shortcuts that I recognized, or new shortcuts that I might take advantage of, or maybe their professions don't have shortcuts, So the book is sort of interspersed, the mathematical kind of side, with conversations I had with different practitioners, an international cellist, walker and a mountaineer, therapist, and various other professions, sort of exploring the role of the shortcut in their work too. So it's very much a celebration of mathematics, but also a kind of interesting exploration of the shortcut beyond my world of maths. So there's a little introduction.
Great, that was great. And that's what the book is actually about. it's a wonderful actually book for old people like me and for young people. I mean, I had heard of some of the shortcuts in the book, but having them all together put together actually helps me to think about it. For young people, this is a great book because I think it doesn't explain everything. So you get kind of tantalized by it and you probably want to read some more. There's a lot of anecdotes about you, which is fun, but not cringing anecdotes. So I wanted to talk about, one of the things that you talked about already was that, you know, when you were a young mathematician, you had a math teacher who told you about shortcuts, but before you were a mathematician, you write in the book that you wanted to be a spy. And then in order to be a spy, you would have to learn different languages, you know, Russian, I guess, Russian, German, given your age. And you tried to learn languages and that you were just not very good at it. And that led to the question about shortcuts. There's been a sort of an idea that was made public by a writer, Malcolm Gladwell, saying that, you know, if you do 10,000 hours of work on something, you become an expert. And your question was, is it true, or are we made differently? You actually talk about, you know, are our brains at birth different? So for instance, can anyone after 10,000 hours be a grandmaster, et cetera? And I thought that was kind of interesting because you sort of talked about, there's no shortcut. You said you took up the cello at the age of 45. Is that right? Something like that. And
yeah, something like that.
And you're still not very good? No, sorry. I don't know, but that it doesn't seem like 10,000 hours is, you don't become Jacqueline Dupre after 10,000 hours. So the question I have to you is, what do you actually think about that? You sort of alluded to the fact that you don't believe in the 10,000 hours, but you also think that it might be something that happens at birth. But the brain is plastic, right? So
yeah.
So talk more about that.
Well, first of all, yeah, you've already highlighted an interesting thing, which is, I think, you know, if you're going to learn the cello, you know, why couldn't I find some shortcuts? I went to talk to Natalie Klein, who's one of my favorite cellists, hoping that she was going to give me some great shortcuts in order that I could become a wonderful cellist. And she said, well, I mean, there are some shortcuts, and that's why we learn our scales and arpeggios, because that allows us to see certain patterns in music, and we can play those very quickly because they're under our fingers. She said, compared it a little bit to a reading, that we don't read words letter by letter, but we see a word in totality. And in a way, that's a certain sort of shortcut that musicians will use. They'll see patterns and they'll be able to just play those patterns without having to analyze single notes. But she said there's nothing, you can't get away from the fact that when you're practicing the cello, you are trying to get a muscle memory very often. And this seemed to be one of the key hindrances in finding shortcuts, is if you have to change the body physically in some way, then it's very hard to actually shortcut that. So in order to play a piece and get the fingers moving very, very nicely when you're playing a Bach suite, there seems to be no way to for the substitute of actually getting your body to change itself physically. And she compared herself a little bit to being an international athlete, that yeah, you could take drugs and things like that might help you to improve your physical abilities, but there's nothing really you can do other than actually doing that training. And I suppose that's also the point about learning a language. So I actually talked to Ed Cook, who's a memory champion. I didn't realize there were such things, but he's also set up a company trying to help people to learn languages, and he's trying to find what are the shortcuts that can help people to you know, get a certain expertise in a language quickly. But you know, again, you're really trying to change the brain structure, and that, as you say, it is a plastic object, but the plasticity requires reinforcement of a word and its meaning, and so it seems that there's little you can do to avoid quite a lot of the hard work of learning a language. But he did give some interesting tricks, which sort of relate in a way to one of the shortcuts I talk about in the book, which is sort of changing language. Sometimes, if you get stuck on something, if you sort of change the language into something else that you're familiar with, then you might make progress. So he sort of said, well, when you're learning Russian, if you've got a new word, and it just has no resonance for you, then change that, try and break that word into pieces, which then you can make some sort of false emotional connection with. It might remind you of something else that's similar. And so he was almost using the fact you need to translate it into something that you've already got in your brain in order to be able to make that to try and establish that connection with this new word. So I think people probably do this automatically anyway, that they hear a new word and it sounds like something familiar, and that will be the help to log it into your brain. But I think he again couldn't really offer me too much more other than doing the kind of hard work of reinforcing the patterns in the brain that are being developed. But you referred to this idea that is a brain somehow born with certain abilities, and this I found rather disturbing in a way. But I talked to a neuroscientist as part of the book, who indeed wanted to be a grandmaster at chess. He put in the 10,000 hours. He went to Russia, trained with all of the great teachers, and he couldn't get past kind of master status, which is still pretty good. But whatever he did, he couldn't seem to shift himself into the kind of top realm. And so actually he started to say, well, why is that? What is stopping me? And he then got quite interested in the nature of the brain. And it turns out that the grandmasters are literally making shortcuts in their brain. They seem to have a brain sort of connections, which mean that they almost do less thinking. So actually I did an experiment where I was wired up and I was playing chess, and this neuroscientist could see that I was overusing my brain because I was kind of thinking of what the implications were of all the pieces. And I was playing a grandmaster who was being scanned at the same time, and his brain activity was so much less than mine. And it seemed like it was almost like an intuition that he had for how to play this thing. So it went through a much less conscious process. Now, the controversial thing is the neuroscientist that I interviewed believes that is not something which is learned, but is actually a property of the brain that's there very early on. And his kind of work was trying to then identify, well, your brain may not be well wired for chess, but maybe for mathematics, you've got this kind of very fast shortcuts that you're making. So I think the jury's still out about, is this something which is, there in the structure of the brain early on, or is this something you can learn to do? He felt that it was something he couldn't break down the network in his brain to be able to tap into this kind of shortcut thinking that the grandmasters was doing.
So speaking of brains, you speak about Gauss's brain. Gauss was a great mathematician and physicist. Where is Gauss's brain? So you say that when Gauss gave his brain to science when he died, and that they studied it, but they didn't have such good machines to look at it carefully. And after they studied it, they seem to have mixed it up. Is that?
Yeah, it's very easy. Well, just to say, Gauss actually is a companion throughout this book, because he begins the book with that lovely little story, which is probably mythical. It probably never happened, but we love telling it, of him in the classroom. But I kept on finding that he had a part to play in so many of the shortcuts that I talk about in the book, that I sort of decided to almost use his biography as a useful glue throughout the book. And so it ends actually, the neuroscience chapter I talk about is towards the end. And so I thought, well, we'll end with his death and the fact that he donates his brain to the the university in Göttingen where he was based. And yeah, so they did start analyzing, was there something special about his brain that meant he was just such a great mathematician, so good at shortcuts? And it said that his brain was more, had more folds in it than a regular brain, as if it was kind of using some clever fractal quality of folding that meant that it could make these connections faster. But the weird thing is they then mixed his brain up with another scientist in the university. And it was only very recently, so they actually did drawings of the brain, and then they got mixed up, and they were trying to analyze this brain with new technology, on modern day scanners and things, and it just didn't match the illustration. And they realized just recently that these two brains had got mixed up. So we now know which is Gauss's brain, thanks to the little kind of lithogram that was done very, very early on. But so the brain is still, I think, in Göttingen, ready to be brought to life again. I don't know, but
So one of the other things you talk about, which I'm an experimental physicist, so we think a little bit differently, is about diagrams in equations. And in the end, you like the equation. I noticed there are some diagrams in your book. I'm lazy also, so I often want diagrams instead of words. But you say you don't trust diagrams completely. But isn't a diagram a shortcut? So for instance, let me just give you an example. In physics, we have this description of the world, the standard model, which is a very complicated equation. But then there's these Feynman diagrams, which are very, very simple. And they actually fit in our brains. That is, it's easy to think about them. Whereas the equation, it's less easy. So I'm just wondering, is a diagram a shortcut?
Absolutely. And so one of the chapters is called the diagram shortcut. And, I certainly celebrate the story of Feynman coming up with these amazing little pictures that you all draw on your blackboards, whiteboards. And that is a beautiful example of the power of a diagram, because without those, you have to do these complex path integrals. It's just very heavy equations, which you quickly lose sight of what's going on. But the beauty is you translate it into these pictures, these diagrams you produce, and suddenly you're able to manipulate and understand how these things interact. So I think the very interesting thing about a diagram, of course, is that it's very close to cutting corners, because it's about throwing away information that's not important to the problem at hand. And so that's a real skill, how much information is not necessary in order to be able to understand what's going on. Another beautiful example of the power of a diagram was the diagram that Crick and Watson published in their Nature paper, which was the discovery of the double helix structure of DNA. Their first attempts at drawing this, I've seen them in one of the museums here, is incredibly complicated, because they wanted to include all the other amazing stuff they discovered about the structure of this molecule. And it was just obscuring this beautiful, simple structure that they discovered, this double helix. And so Crick actually took the drawing he'd made back home and showed it to his wife, Odile Crick, who was an artist. And she said, well, you don't need all of this other stuff. It's just getting in the way. And she drew this double helix structure. And it's actually Odile Crick's picture that is in the Nature paper. And she was able to kind of distill the essence of what was going on in this case. So, and I think actually, another sort of shortcut is the idea of topology over geometry. The idea that topology is a sort of bendy sheet geometry. It's about how things are connected together. So very often a topological map will be much more helpful than a geometric map. So the London Underground map that very iconic map that's been replicated in many cities, sort of using the idea that I only need to know how the stations are connected together. I don't need to know what the actual distance is or how they're physically laid out. And it's weird, if you look at a geometric map of the London Underground, you would not recognize it at all, and it's completely useless to use it. So So I think that's, a very interesting sort of challenge is, well, okay, what do I not need to know so that this diagram actually becomes a powerful tool in order to be able to do things? And there's a very nice Lewis Carroll story, and in fact Borges uses the same idea of a land which decides that the map of their country is going to be perfect. It's going to be a 1-to-1, 1 mile to 1 mile representation. They're going to have every single detail of all the buildings, all the roads. And in the Lewis Carroll story, when the person says, well, have you ever used this map? And they said, well, no, the farmers objected to it being laid out because it covered the whole of the country. And then, frankly, we find the country as a good a map as the map we've made. So we just use the country as the map itself. So there's an example of, well, that's really silly. You've not thrown away anything and the map is useless. But that said, a diagram can be dangerous because, first of all, you can throw away too much information, and therefore there's a danger you mislead. So I give some examples of bad graphs which seem to be telling one story but are actually telling a completely different story because they're drawn badly. But you also mentioned I like equations, so I think that mathematicians divide into two camps, and I wonder whether this is also true of physicists as well. But I think there are those that like to use equations. They use language to try and explore things. And then there are mathematicians who love drawing pictures, and that's their way to insight. So, for example, my colleague in Oxford, Roger Penrose, he loves drawing. He loves making pictures of twistor spaces. And then other mathematicians turn that into kind of a kind of language or an algebra. I'm more somebody who likes exploring my mathematics, which is the mathematics of symmetry, through language rather than picture. And I find very often a picture can obscure what's going on, especially if you're working in high dimensions. A picture is going to be useless. You have to use language in order to be able to describe a 8-dimensional symmetrical object. You try and draw it, you're going to be taking a projection, a shadow of it. It's just going to lose information. So I think it's very much message of the book is each problem you need to analyze what sort of way of approaching this, what shortcut is going to work. Maybe a diagram will work, maybe a diagram isn't going to work in all cases.
So you also talk about you talk about a lot of shortcuts. You talk about shortcuts in finance, in at Google, in their search engine, which was very good because it told my students that they needed to learn linear algebra. You talk about behavioral therapy, cognitive behavioral therapy as a shortcut. So could you just define shortcut a little bit? Because here's the real question. The real question is, there are many shortcuts. Not all of them are interesting, I'm guessing. If I think, can I do a shortcut to the Rubik's Cube? That doesn't seem very interesting. Maybe it is in mathematics, I don't know. But you've chosen shortcuts that teach us something. But I wonder how many shortcuts there are that don't teach us anything. And then I'm just interested in this idea of what exactly is a shortcut, and is for instance, in psychotherapy.
Yes, I think certainly I've celebrated the shortcuts, which I think we're very proud of. They're clever ways of looking at a problem. I wanted shortcuts which give you that kind of aha moment of, oh, I see, that's so much better way of thinking about this problem. And so actually I start each of the chapters with a little puzzle to try and get the reader's kind of juices running in their brain and thinking, okay, yeah, well, there's a hard way I can see how to do this. So, but clearly this chapter is going to help me to find a cleverer way to do this. I mean, for example, here's a little challenge. If you've got 10 stairs and you're allowed to climb the stairs 1 or 2 at a time, how many different ways are there to get to the top of the stairs? So the long, laborious way is trying every single possible way. Okay, I could do 1 step at a time, or take them 2 at a time, or a combination of those. And clearly that's going to you probably miss some, you might repeat some. It's in a very inefficient way. So for me, a shortcut is, well, what's a better way of thinking that problem, which is going to allow me to get the answer without making all of these errors on the way? So I think that trying to think of this in a kind of landscape way, you know, there's a very long journey I could make, and it's very boring, and there's no views on the way. It's going to take me days to get to my destination, or else there's a, you know, little sign saying shortcut this way, and that way I've got some really beautiful views. It gets me to my destination in a fast, efficient manner, so I can do what I want to do when I get there. So I think that you're right. There are some shortcuts which are perhaps not so interesting, but that's also fine. I mean, again, let's come back to what the point of these shortcuts is. These are not meant to be stopping you doing things you enjoy doing. I mean, I talked to Robert McFarlane, a wonderful writer about walking and mountaineering, because I was quite intrigued what his relationship to a shortcut might be, because here's somebody who goes out and wants to spend days walking up mountains. So, you know, a shortcut for him, what's the point of taking a helicopter to the top of the mountain? That is a shortcut. But for him, it's a totally unsatisfying shortcut. But I think that's illustrates now that difference of Aristotle's between praxis and proesis. No, he's actually doing the work because he enjoys being in the moment. I mean, there's sort of no point to shortcutting listening to a piece of music. You want to experience it in time. So, however, if you want to, for example, see whether you want to watch a film or not, a trailer might be a useful shortcut to get a quick feel for what the film might be like. So there are all these different range of shortcuts. Now, Robert McFarlane actually did have, he said, it's not like I don't like shortcuts, because actually he had to use one rather dramatically. He was up a mountain, and I learned this new word from him, actually, benighted. They were about to be benighted, which means the night is about to come in and engulf them. And if they were up on the mountain, it would have been very dangerous. So he had to get off the mountain very quickly. And so he said, well, we decided there was snow on the mountain. So we created an avalanche, which we rode down to the bottom of the mountain safely. And we got off the mountain using an avalanche as a shortcut before they were benighted. So that was a rather curious one. But yeah, you mentioned therapy, because my wife's a therapist. She's a psychologist, and she actually hated the idea of me writing this book. She said, no, she likes slow cooking. She likes taking time over things. And in particular, she believes that quite often, if somebody's coming to therapy, again, it takes time to sometimes undo trauma that has happened in childhood, for example. In fact, I talked to Susie Orbach, who's a very famous psychologist here, who treated Princess Diana when she was suffering. She said it's a little bit like unlearning your language. You know, just imagine unlearning English. You know, it's hard enough learning a new language, but imagine trying to unlearn a language. That again takes a lot of time. So there's some therapy that, frankly, you cannot avoid the hard work. Again, goes back to you're changing your body. It's very difficult, can take a long time. However, there are some sorts of therapy that do access amazing shortcuts. The discovery of cognitive behavioral therapy, which is an understanding of thought process in the brain being a little bit like an algorithm, and sometimes the algorithm can keep on taking you just to a bad place. But if you understand that there's one key thing in the algorithm, that if you change that little bit of code, you won't end up in this bad place. Cognitive behavioral therapy is trying to lift you out and look at that thought process and understand, well, sometimes thought processes are pretty simplistic, and you can intervene, and with 8 weeks of therapy, actually change the way that you're following through that algorithm, such you don't always end up in a bad place. So it's that, I think, is a very powerful example of looking at thought process as an algorithm. And actually, again, diagrams are an incredibly important role in cognitive behavioral therapy. To actually see your pattern of behavior on the page can quickly allow you to stop falling into patterns of bad thought.
I think we had somebody giving a talk about habits, a scientific talk about habits, and saying they were incredibly hard to break, that it takes a lot longer than 8 weeks. So I'm wondering whether it's not really the habit that you're breaking, but just you have some insight in this case, or whether it just doesn't work. I don't know.
Well, I think, it's interesting. I think some habits are very hard to break because they're, if they're complex thought processes, which are just meaning you're doing this thing over and over, then that, you've got to rewire the brain, and it is plastic, but if the wiring is requiring quite a lot of, time, then that's hard shortcut. But sometimes I think you can get a meta view of your thought process and help yourself stop falling into these patterns.
Yeah, no, I think you're right. So you do another couple of examples, which I wanted to ask you about, because you talk about, financial advice and how to win at the stock market, which is interesting. And what are the shortcuts there? And I'm sure everybody will be interested in those. But you have two views of it. One is you say, at hedge funds, there's a lot of mathematicians and physicists who know a lot of things, and they use information. For instance, they bet on 2 things out of 3, so that they'll make some money in the end. And then you talk about another financial analyst who uses history, who was a history major, and who looks at companies and looks at the history of the company and sort of uses that as a shortcut to know, what to bet on. My question is, for you as a mathematician who likes equations, who are you going to choose for your financial advisor, the historian or the hedge fund?
Well, I think the interesting thing is to choose a company which has both, frankly, because its combined ways of thinking can be very powerful, and actually that's sort of one of the kind of messages of the book, is that collaboration is often the best shortcut to you don't have all the tools, find somebody who has different tools, and together you can make progress. So I think I was quite struck by talking to this financial analyst who I knew wasn't mathematical. I mean, she'd done a history degree, so I was kind of intrigued. What are you tapping into that is obviously a different sort of approach to, but in some ways it's something I did recognize, because it's sort of about pattern recognition. So what she does with a story is the fact that she's starting to understand that this story is a story that she's heard already about a company, and she knows what the ending is because she's seen it in other stories, and that's about recognizing this company is falling into a pattern of behavior that I've seen somewhere else. And so for me, that's a very powerful shortcut in mathematics, is the power of finding a pattern in whether it's data or numbers or in the behavior of something, such you can then take that and then predict what something is going to do in the future. So I that was what was very striking, that often I would talk to somebody and at first sight the shortcut that they were talking about sounded very unlike anything I knew, but then when I thought about it more, I realized, oh no, there's something to this which I recognize. And another one was I talked to somebody who's great. He created a great startup called lastminute.com, which is basically, I'm not sure whether you have it in the US. It's basically where you can book hotels and flights at very short notice. And I asked him, well, what was his shortcut to becoming incredibly successful as an entrepreneur? And he said, well, my shortcut is flying very close to the law. So basically, I'm breaking the law in order to make this company when it was first formed, because I was sweeping data online, which was actually illegal at the time. And he said many of the startups that have been successful, Airbnb, that was actually breaking a law about the use of your house as a kind of place that people can come and stay. So he gave me quite a few different examples of companies that were breaking laws, and And then I realized actually that's a good shortcut in mathematics as well, because one of the best shortcuts we came up with was inventing this new number, the square root of -1, imaginary numbers. And that was kind of breaking a rule, because prior to that, mathematicians said, well, if you square a number, it's positive. Plus times a plus is plus, minus times a minus is plus. So, what is this number that you're trying to use called the square root of a negative number? But that kind of breaking that law and sort of bursting mathematics into a new realm actually became a very powerful shortcut. Using imaginary numbers, complex numbers, you can do calculations and things that would take you forever in real numbers. I mean, radar, for example, in the past, computers weren't fast enough to work out where the planes were in the sky using just conventional mathematics. But if you use complex numbers, suddenly they had access to being able to do these calculations and find out where the plane is before it had crashed. So it was very interesting. Many of the people I talked to, although the shortcuts that they were using at first sight sounded very alien, they actually resonated quite often with things that I recognize in mathematics.
So it's kind of interesting. I'm teaching complex numbers now to my students to do basically something like radar. But I didn't think of it as a shortcut before. I just thought of it as very cool. Yeah. So you talk about this idea that, science or perhaps mathematics is often done by more than one person at a time. And you talk about a very nice story about Weber and Gauss, yes, where they strung a 3-kilometer wire between their houses.
Yeah. I think between the labs or something.
Between the labs. In order so that they could talk to each other and collaborate better. But did they ever come up with a shortcut together?
They first of all had to produce a code that they could use on this wire, because they were basically using electromagnetism to communicate with each other. I mean, this was sort of, you could say, the internet started in Göttingen with Weber and Gauss, because they strung up this wire and were using electromagnetism to communicate between themselves. But they did come up with this shortcut of a code that was I think it was their own personal code, but it was sort of like an early forerunner of things like the Bordeaux code and like Morse code and things like that. But yeah, I think that was a great example of the fact that one person on their own will often get stuck on the way, and in order, a good shortcut is often having a good collaborator. I mean, I find that very often I have very key collaborators around the world that we'd never get to the top of the ladder. We somehow eat individually because we each have our own sort of rungs that we add to the discovery. I'm sure you find that as well. It's sort of in your subject you have huge teams, I think, responsible for the discoveries.
We have huge teams, but we don't have wires between us. I was just that was in Göttingen, right? That was in the town of Göttingen in Germany, and yeah. I was wondering whether that wire went over David Hilbert's house, where he had an outdoor blackboard where people would come and talk. But I think you're saying it's between the two labs, so maybe that doesn't work.
Yeah, and I suppose the David Hilbert is maybe some decades later. So whether the wire was still there when David Hilbert was showing off his blackboard in his garden, I don't know.
So I have one more question for you, which is very, very short, but then we have some questions. I just want to know this because you talk about, in this 10,000 hours story or using data to make decisions, you talk about two cardiologists. One has his statistics of how many operations succeeded and what techniques he does. And the other one says to you, I'm very creative and people are very inspired by me. And you don't go any further than that. I think you think it's obvious which one you would choose, but actually the second one is sort of the definition of the TV character House. So I was just wondering which one you would choose.
Well, I would go for the data one because, but that said, again, it comes back to the best thing is to have multiple ways of looking at things. So I would love to find the one who is able to use language in that sort of creative way to big up what he does or she does, and also can back it up with good data as well. So I tell a little story about the fox and the hedgehog. That I think there are two different sorts of thinkers. The hedgehog knows one thing in great detail, whilst the fox is sort of knows many things in a shallow way. I think both are useful, but the best thing is to have a combination of both a fox and a hedgehog at your to be able to get advice from.
Okay, so we now have from the audience, Elena Rubenstein asked, do we inherit the brain capacities that were acquired by our ancestors?
Well, this is a huge amount of debate over how much actually do we take forward from our brain structure from before. And, there's a very interesting thing about language, because, and this actually related to the artificial intelligence book, because the way AI learns language, for example, is to be exposed to a huge amount of data, and then it understands how to put words together. But we were very struck by the fact that a child does not need to be exposed to much data before it actually starts speaking language. So it's very clear, this is what Chomsky talks about as well, that the brain actually becomes pre-programmed for language. So there's clearly, this is not machine learning. It isn't sort of blank slate that then exposed to a huge amount of data then starts to learn language. No, it's coming already preformed. And so, I often am asked, what about mathematicians? Are they born, or can you become a mathematician? And I think, with all of these answers, it's a combination of the two. I think that that there's a lot of evidence that mathematical parents probably will produce a child that very quickly picks up mathematics, that it seems as if some hardwiring is already established there that just needs to be kind of sparked up by an environmental sort of nurturing. But that said, if you haven't had that, I think that, yeah, maybe it takes a little bit more of those 10,000 hours to mark out those new pathways. But I'm a big believer in no, you don't have to be born a mathematician. And I think you spend time in this world of mathematics, then you can get the kind of maturity to actually be mathematical. I mean, clearly there are some people who have a problem like dyscalculia, which actually is the fact that their brains are having difficulty dealing with this kind of number calculations, but that can often push people into, mathematics is not about calculation. So dyscalculia doesn't mean that you won't be a great mathematician. Maybe you'll choose mathematics, which has a much less numerical kind of sort of approach to it.
So here's a question that I really want to know the answer to. Someone asks, what can we do to make these kind of mathematical shortcuts and math in general more widely understood and utilized? And are there steps you'd recommend to teachers and professors to help them make math more accessible and appealing to their students?
Yes, I mean, one of the things I think my teacher did for me, which was really helpful, was not to shy away from kind of big ideas. And I think that's, I often feel like mathematics, actually all we're doing is kind of doing the scales and arpeggios, and nobody plays us any real music. So my feeling is I'd love the curriculum to include not just the technical side of mathematics, but for example, talking about the concept of infinity and the fact that there are many different sorts of infinity, some bigger than others. The fact that you can use coordinate geometry to make 4-dimensional spheres or 5-dimensional cubes and explore them. I think kids would actually respond to seeing these big ideas and kind of, almost like science fiction stories about these kind of high dimensional objects or infinities. And that would hopefully motivate them to learn the more technical side to be able to fully master those things. But I've often suggested to government here in the UK that we should have, we have one exam in mathematics that students do at the age of 16. But in English, they have two. They do English language and English literature. They're allowed to, they have to learn how to spell and grammar and things like that. But they also have an exam where they get to read Shakespeare and George Orwell and romantic poetry. And I wish that we had actually two kind of courses in mathematics. One, the technical side, which is kind of the bread and butter of how to do calculations and things. But then another sort of course, which is about these big stories, the kind of Shakespeare of maths, the Mozart of maths. And that I think would actually turn students on to just the power and the magic and the beauty of this subject, which will then hopefully inspire them to do the more technical side.
So I just a question. I mean, I like this book. I think young people reading this book, like I probably would have become a mathematician. There's a young man here who's now a graduate student at MIT who writes that you came to his high school in Hong Kong and totally got him interested in math. And now he's doing that. You can read it later. But books aren't necessarily the only way to do that. Are you considering? Do you ever consider just making a series of videos or?
Well, I mean, there is a wonderful YouTube channel called Numberphile, which I've made a few things. I just made a little film about Bach's use of shortcuts to create amazing music. He writes these little puzzle cannons. So people should certainly check out the wonderful films that are made on Numberphile. But actually, one of the things I'm really enjoying at the moment is using sort of different disciplines to try and explore mathematical and scientific ideas. So it was mentioned in the introduction that I wrote a play which I performed in. And in this play, we explore the idea of cyclical universes, the idea of infinity and finiteness. And so that's an exciting way to actually bring mathematical ideas to perhaps an audience that wouldn't normally think about sort of approaching science, a theatrical audience. The other thing is music. I run a center called Prism, Practice and Research in Science and Music in Manchester, using the idea that, mathematics has a lot, of course, to do with music, but not just the fact that rhythms and harmony, but actual structure of music has a very mathematical nature to it. So I think these are really exciting ways to try and bring kind of mathematical ideas to an audience that wouldn't normally be thinking about doing something about mathematics.
So there's another question, which is, what was the most surprising thing you uncovered when researching this book? And let me add to that, did you find all of the shortcuts? Are there any left? And what was the most surprising one that you found?
Well, I think curiously, I think the most surprising one was the realization that mathematics is sometimes good at showing there are no shortcuts. I think that was, I was expecting to tell lots of stories of shortcuts, but the final chapter is actually the understanding that we now think that there are some problems that we will not be able to come up with some clever way to solve them. Now, for me, that's a really interesting challenge. How do you prove there are no shortcuts to a problem? So the classic one is the traveling salesman problem. So you have a map with lots of cities and roads joining the cities with distances on them. You've got to find the shortest path to visit all of the cities. We think that problem has a quality that you cannot find that shortest path other than by listing all of the paths possible. There seems to be no algorithm that will just pull out the shortest path without doing any hard work. Now, I think that's one of the rather curious qualities that mathematics has, that it's able to almost turn on itself and show its limitations. We don't know whether there is no shortcut, but that's actually one of our greatest unsolved problems at the moment, is to prove whether the traveling salesman problem is genuinely something which you cannot avoid doing hard work or not. And it's a problem called P versus NP, and there's $1 million prize actually for anybody who can show there are no shortcuts. So that for me is quite exciting. And you know, I suppose Fermat's last theorem is another example of mathematics showing there are no solutions to this equation. You know, that's really difficult. How do you show? It's easy to find some numbers and plug them into an equation. How do you show that there are no numbers which will solve this? And I think even something like Gödel's incompleteness theorem, a wonderful example of mathematics looking at itself and saying, hey, there are going to be some true statements about numbers which we are not going to be able to prove are true. So this is rather exciting, the way that mathematics can look at itself and sometimes show its limitations.
I really like that. That's a good way to end, because the Millennium Prize, that's what it's called, the prize that you get, the $1 million. I think that's a good reason for young people to solve it.
There are lots of problems out there we can't solve. So it's the next generation. Those guys at MIT, at Harvard, you know, we're waiting for you to come up with the next shortcuts that we've missed.
Anyhow, thank you so much. It was great. It was great reading the book. It was great talking to you. And thank you so much for being here.
Oh, thank you for inviting me to join you at the Harvard Bookstore virtually in Harvard. So thanks a lot.
Okay.
Thank
Goodbye,
you so much,
everyone.
Marcus and Melissa. That was fantastic. And thank you to all of you for joining us tonight. I just want to stress, please check out this fantastic book and purchase Thinking Better at harvard.com. And on behalf of the Harvard Bookstore, the Harvard Library, and the Harvard Division of Science, all here in Cambridge, Massachusetts, have a good night. Keep reading and please be well. Thank you.
Bye.
Bye.